Hello everybody. So this is our third lecture, and so our course, the title of our course is Computational Gas Dynamics. So the first and the second lecture were about gas dynamics. So we discussed the subject. So what is gas dynamics, Euler equations, and also the previous lecture was dedicated to analog equation, just scalar conservation law. So just a quick reminder, right? So this is a scalar conservation law written in conservation form. This is quasi-linear form. Oh, I have a pointer here, but it doesn't work. This is a conservation form. This is quasi-linear form, and we specified this function, lambda, as u, or equally f equals to u squared over 2, and this equation is called a Hopf equation. And we discussed that this is the simplest possible, but at the same time non-linear equation that mimics the many properties of the whole Euler equations. We discussed, and so you should know actually what does it mean, characteristics of the nonlinear scalar conservation law. I mean this equation, what is gradient catastrophe. So we discussed the mechanism how the shock waves or discontinuous solutions can appear even if you have very smooth initial data. So here u is our function, psi is initial data. And we discussed that for scalar conservation law characteristic lines, they are straight lines. And in the region where the psi function increases monotonically, then we have the divergent behavior of our characteristics. And in the regions where psi function decreases monotonically, we have the convergent behavior of our characteristic lines. And in this case, for sure, we should have situation when characteristic lines intersect. But the characteristic line is the line along which our solution propagates. And it means that at the point when the characteristic lines intersect, we do not know the solution. Because on one hand, one characteristic corresponds to one solution, another to another. And the only way how to resolve this situation, this issue, is the formation of a shock wave or discontinuous solution in simulation, or from theoretical point of view, doesn't matter. But if we want to consider shock waves or discontinuous solutions, we should take into account, introduce so-called weak solutions. So weak solutions are the solutions that fulfill not the differential but integral form of equation. And we discussed Ryabenkii-Hugoniot jump conditions. So parameters to the left and to the right of discontinuity, they cannot be some arbitrarily. So there should exist some relationship between parameters to the left, to the right, or in front of and behind of discontinuity and the speed of this shock wave. And we derived these Ryabenkii-Hugoniot jump conditions for the Hopf equation. And we finished our previous lecture with the consideration of Riemann problem for the Hopf equation. So Riemann problem is the Cauchy problem with the discontinuity in the initial data. And later I will explain why is it so important. But anyway, from theoretical point of view, we considered the possible solutions for the Riemann problem for the Hopf equations. And we discussed that we should add some additional condition called Lax entropy condition to choose the correct solution of the Riemann problem in case when the u was equal to 0 here and 1 here. So it was less to the left part of discontinuity. So this is the reminder of previous lecture. And now we want to move towards the understanding how to compute this solution. So okay, the reality is that we need how to solve these equations because they correspond to real flows of gases or other media, compressible media, and we should know how to compute these types of flows. And that is why the topic of today's lecture is basics of finite difference schemes. So I think that you may know a lot of things that we are going to discuss today, but anyway, I'd like to add some, mathematical strictness of these topics. And today we will start even not with partial differential equations because they are much more difficult. Today we are going to start just with ordinary differential equation. Moreover, with linear ordinary differential equation, and even not with system, but just with one equation. So again, I am also preparing two lectures for bachelor students, and although it will be in Chinese, in English, the English is poor. That is why I try to duplicate the titles in Chinese as well. So consider the initial value of Cauchy problem for the linear ordinary differential equation. du over dx plus a equals to 0. So u is a function, a is some constant. And we want to solve this, and so we know that u of 0 equals to b. So this is the initial condition. And we want to solve this equation in the domain as a segment from 0 to 1. You may know, you must know, you should know from your mathematical courses that the exact solution for this problem is known. So the exact solution is b multiplied exponent function to minus ax, because we can just move this au to right hand side and then so just resolve this equation. Indeed, if x equals to 0, then exponent to 0 is 1, then u exact of 0 is b. This is the initial condition. And we can just, for example, choose constant b equals to 2 and a equals to 3, just for example, right? And plot this curve. I took this plus a and a greater than 0 to have some decreasing solution, because I taught to you on the first lecture that one of my field of interest is numerical simulation of flows with chemical reactions. So this model is very simple analog for equation for chemical reactions. But in chemical reactions, your mole fraction or volume or mass fraction of your component decreases in time if you consider, for example, reactant component. And that is why we're interested actually in consideration of decreasing solution. For example, not increasing. And in principle, the the solution that increases with the exponent function is not physically relevant actually. Okay, so the beauty of this model is that we know the exact solution, and we can compare our numerical solution with this known exact solution. Let's propose the simplest possible numerical scheme for the solution of this problem. If it would, I would ask you, so what is the simplest possible finite difference scheme, even if we even do not understand, and even if we are not able to explain mathematically what does it mean. So the obvious idea is that we should just substitute this real derivative with some finite difference. So we should substitute du over dx with difference between 2 points, ux plus h minus u of x over h. And we understand that actually if h is small enough, so h here within the scope of this lecture, h is very small, so it's significantly smaller than unity, than 1, something like 0.001 and so on. So if h is very small, we can expect that this value looks very close to the real derivative, right? But for that, actually, we should introduce another concept of computational grid. So we should subdivide all our segments from 0 to 1 using these nodes, xn equals to nh. For example, let the computational grid be uniform. So it can be non-uniform. For example, if we know that in some region we have the very sharp changing of our function, we can consider more detailed computational grid. But suppose that computational grid is uniform. So h equals to 1 over n, where n is the number of segments on which we divide our segment from 0 to 1. So xn are the coordinates of our nodes. Okay. And now we introduce the grid function. So now u sub n is the numerically computed grid function. So n means that we compute our grid function at the node with the number n. So for example, if n equals to 1, it means that we try to find u1 using u0, and u0 is the initial condition, and so on. So let's write it down. So we can express un as a function of un minus 1. So in turn, un minus 1 is the same function as argument un minus 2, and so on and so forth. And so we go to u1 equals to 1 minus ah u0, and then we can put this term to here, this to here, and so on, and collect them into one formula. If we do that, we can see that u sub n equals to this function. We can see 1 minus h to nth power u0. But we know u0. u0 is just our initial condition, b, here, initial point. So the value of the function of x equals to 0. And n equals to xn over h. So if we believe that our computational grid is uniform, we get the exact formula for our numerical solution. So for each n, 1, 2, 3, and so on, we can compute the value un. So for sure, it's possible to do that only for a very simple case. So if our numerical scheme is very simple, so just, Euler scheme. So this scheme is called explicit Euler scheme. Maybe also you know that there should exist implicit Euler scheme. We will also discuss it later. But anyway, as soon as our scheme is very simple, we can get the analytical solution of this finite difference equation. And so we can ask ourselves a very simple question. So okay, we know the exact solution. So we can take just one point, for example, x equals to 0.5, and we know the exact solution. It looks like this one. And at the same time, as a result of application of finite difference scheme, we know the numerical solution. Can we compare the numerical solution with the exact one? How can we do that? So this is the numerical solution, this is the exact solution. At this moment, we compare it only in one point. For sure, we can predict some problems because we have not one point, we have many points, and we will discuss what should we do with that. But now we can compare it only in one point. For that, we can compute this difference, delta. Let's compute the difference, u of xn minus u exact of xn, and just put these terms here. The standard, the common apparatus how to do that is the usage of Taylor series expansions of the function. So we believe that if we, at some point, we can express the function in the vicinity of this point as a Taylor series expansion. So for that, we believe that h is very small. H is less than 0. So we can use the Taylor series expansion for this 1 minus ah xn over h. This is called the basic logarithmic identity. So from, even from school, you should remember that 1 minus something small to the power 1 over this small equals to this exponent from logarithm. And then we can use Taylor series expansion for logarithm and then for exponent function. So this is just a reminder, again, from the first year at university, that this is the Taylor series expansion for logarithm, where x is a small value. And so we substitute logarithm 1 minus ah using this formula. So here, not x, but minus ah. That is why is minus ah minus the second power of this term plus big O of h cubic. So what does it mean, big O? It means that something O of h to third power means something that if you divide it over h to the third power, it will be something constrained. So it's sort of some constant multiplied by h to the third power. And then we should open the brackets. We open the brackets and get the multiplication of 3 exponent functions, and then we use the Taylor series expansion for the exponent function, like this one. So it's very simple, just the summation of x over x to nth power over n factorial. Actually, this is the common approach how to explore, how to study the properties of numerical methods. So we substitute these. So we use this Taylor series expansion for this exponent and for this exponent. Then we also multiple. We also open brackets and get the final formula. We skip the terms, so not skip, but we know that, for example, big O of h squared multiplied by big O of h squared is the terms with for example h to fourth power we do not take into account, so they are all inside here. So everything that is smaller than this term, everything is inside this term. So we can see that after this procedure, this numerical solution is like exact solution, right? So we skip this b and consider only this term, and we can see that it's exponent function, like exact solution. So this numerical solution behaves like exact solution plus something else. It means that our delta is minus h, this constant term, because a constant is constant, b is constant, xn is specific node, exponent to minus axn also constant, plus big O of h squared. But this term is the main one, and it's proportional. So the most important thing is the power of this h. So it's h to the first power. It means that, generally speaking, our error is an order of magnitude of h. So it means that if we take twice smaller step, we will get a reduction our error in 2 times. So it means that the numerical scheme has the first order of accuracy. So the first concept that is very important for us is the accuracy of numerical scheme. So the accuracy of numerical scheme is determined by the relationship between the numerical solution and the exact solution. So if we know exact solution, the error between exact solution and numerical solution determines the accuracy of our numerical method. And you can even now understand that there is some problem, because that usually we do not know the exact solution, right? So that's okay if you know exact solution, but in this case, no need to compute anything. And that is why actually we should think about the another definition for how to check if numerical scheme is good or not. Is it converged scheme or not? Anyway, so we proved that at least at one point, note xn, that the explicit Euler scheme is a numerical scheme of the first order of accuracy. The next lecture, I plan to have some sort of practical lecture. I'd like to just show you how to write the very simple program to compute numerical, to get numerical solutions of the initial value problem for this ordinary differential equation from scratch. And I'd like to show you how to plot these graphs, how to I will show you how to implement different numerical schemes. We will analyze the difference between them, but now the results. So we can plot the exact solution. They are green points. So I just put these points for you to clearly see the difference between the numerical solution and exact solution. So the red curve corresponds to the numerical solution. For example, take n equals to 0 or to 10. So 10 means that we have 10 segments of division of our segment from 0 to 1, right? That is one. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points and 10 segments. And the blue one is the error. So it's the difference between the exact solution and numerical solution. So the left axis is for you numerical and exact, and this is for error. You can see actually this error may be non-uniform, not non-uniform, non-monotonic. Why? Because we have this term, we can have here xn and different constant, and this is also xn exists here, and there's some competition between this linear line and the decreasing exponent and so on. So depending on your specific function, the form of this error can be different. But anyway, what is the most important thing is the behavior of this error and the numerical solution with mesh refinement. So the thing is that our numerical scheme is good if we take n equals to 20, and we expect that our numerical solution will be better. As we can see here, that's true. So the green line is just the same as here, only so you have more points here. And the red curve is closer to the analytical one. And again, this blue line is numerical error. I keep this scale from minimal to maximal the same for all plots, and you can see that, so it's n equals to 40, and so the result becomes better and better, and it's possible to estimate qualitatively. Okay, let's consider, for example, x equals to 0.5, and we can measure the error for this point. It's 0.1101. Then we consider the same x equals to 0.5 for n equals to 20, and you can see it's about twice as smaller. For n40, it's twice as smaller in comparison with the previous case. But actually, it's closer to 2 for this case than for this case. It means that for finer mesh, your correspondence between theory and practice becomes better and better. So for if h goes to 0, you should get just exactly 2. But because of, from theoretical point of view, it's not just h to the first power. So you have also some additional terms. So they are small, but anyway, they exist. But if h goes to 0 and becomes smaller and smaller, so this value is close and closer to 2. So actually, this is the practical proof that the Euler scheme is the first order accurate scheme, because we reduced, so we increased the number of cells or segments twice, and we got this reduction of our numerical error also two times. Okay, so you shouldn't think that these two means that this is the second order of accuracy of method. No, the accuracy is, so the order of accuracy is 1. So actually, all these ideas were formulated many, even not years, but centuries ago. The method under discussion was first described by Leonhard Euler in 1768 in his work Integral Calculus. So he expressed the idea that we can solve the differential equations approximately using this approximation of our derivative. The Euler method is based on approximating the integral curve with a piecewise linear function, the so-called Euler polygonal line. Or quite contrary, we can consider not differential equation but integral equation, but the idea is the same. Cauchy used the Euler method to prove the existence of solution of the initial value problem for a differential equation. So moreover, so you know that a lot of different things in mathematical analysis is connected with the name Cauchy and different limits and so on. But he proved his theorem of existence and uniqueness of the initial value problem using actually this numerical approach. That is why this is actually one of maybe earliest example that even this numerical consideration, or not numerical at that time, it was not numerical, but some approximate consideration for practical purposes also can have some impact on the theories. So we started with that we considered the simplest possible scheme. So we told that, okay, let's take, it's called the forward difference method. So if we had at point x, we took x plus h minus u of x over h, and said that, well, consider, for example, this scheme. But actually, we have a lot of possibilities. So specifically, in our case, we were not able to take the backward difference because we should move forward from left to right, from 0 to 1. But let's make just one step forward. Let's consider some arbitrary function u that is set in a set of nodes. For example, we know u of x minus h, u of x plus h, and the question is how can we approximate this derivative ux? For example, we can do it like this manner or like this one, or using this formula. So we can use this dot point and this point and compute the difference and divide it this distance. So actually, this is one of the first topics of just course on numerical methods, at least in Russia. But it's very important to remind you because so all these things are very closely connected with the topic of approximation. So generally speaking, we can propose that the first derivative of h can be approximated using this formula: 1 over h ux plus h ux minus h with some coefficients alpha 1, alpha 0, and alpha 1. So you can see that all these three formulas, they correspond to this general formula, right? For different coefficients alpha. So this method, this approach is called method of undetermined coefficients. So the idea is how can we find these coefficients alpha to construct to build the numerical approximation with the necessary properties. Here, so the main property is the accuracy order. So how can we find these coefficients alpha to build the numerical scheme of highest possible accuracy for the given stencil? Stencil means the number of the set of points that is used for approximation. Actually, we can do it not for the first order derivative, but for the second order derivative or kth order derivative. So suppose we have this grid function and we want to approximate derivative at this point, and we know values at all these points. Actually, it could be results of your experiment, for example, and you need to estimate the derivative. But so all these questions are connected to each other. And we can propose the following formula. So the kth derivative at node xj equals to 1 over hk, just by analogy with previous slide, and the summation. So L is the number of nodes to the left of our node xj, j, and M is the number of points to the right of this node xj. And alpha, I are unknown coefficients. Many times we will use the Taylor series expansion for the purposes of building a numerical approximation. Consider for the simplicity of the case k equals to 1. So suppose we want to get the approximation of the first order derivative. Then we can expand function ux and Taylor series expansion about the point xj. So uxj plus ih, I mean this guy. Actually, the distribution of points can be non-uniform. We may not have, for example, this point and this point, or maybe we need to construct one-sided approximation. So suppose we didn't discuss, the different boundary conditions. Suppose this is a boundary here, for example, and we need to compute the derivative of function known here, and we know a value here, but we don't have points here, but we have many points here, and maybe we need to construct some one-sided approximation for the derivative. So I mean that this I may be different. We use the same approach of Taylor series expansion. So this is IH here is a small parameter. And in the same manner, IH squared over 2, and so on and so forth. We do not know how many terms should we take. Let's take some n. So this is the last term here. But we know that so there are terms after that. And we should put this u to the formula of the method of undetermined coefficients. Substitute these Taylor expansions into the formula for the derivative obtained by the method of undetermined coefficients. So we put this u xj plus ih to the formula from the previous slide. Then the first derivative is approximated by, and we just have this summation, right? summation for this term, for this term, for this term, and so on and so forth. And then we should have a look on this expression. So to the left, we have the derivative, first derivative of our function u. And to the right, we have this term. And this does not look like a derivative. It's just some combination of values of our u at different points. For this formula of method of undetermined coefficients to approximate the derivative, we should say that this sum should equals to 0. So we should not have this term at all. So the second term is proportional to the first derivative, but we would like to get it. It means that this sum should equals to 1, because to the left and to the right we should have just this derivative. And all the next terms should equals to 0, because we should have only our first derivative. And this is the idea how to build numerical approximations using this approach. So this summation of coefficients alpha should equals to 0, this 1, because we want to approximate the first derivative. That is why this sum corresponds to the first derivative, and all the following terms should equals to 0. Should be equal to 0. So we obtained a system of linear algebraic equations for determining the coefficients alpha I. The number of unknowns is equal to number of equations. So yeah, and here we can understand how many terms should be taken into account for our system to have a solution. So the number of unknowns is equal to number of equations provided that n equals to L plus m. So once again, L is the number of points to the left of our node at which we would like to compute our derivative, and m is the number of nodes to right, and n is the number of terms that we take into account in Taylor's series expansion. That's it. And the second important moment, that we always can solve this system of linear of equations. So actually, this is also another example of the interconnection between different topics of numerical methods course. So, for example, we tried to build numerical approximation to get the formula for first derivative of function. And finally, we deduced this problem to the solution of linear system of linear equations. So that is why we also should know how to solve, for example, system of linear equations, because many problems in computational physics, mechanics, or even just abstract problems in numerical mathematics, finally, to solve them, you should know how to solve just the system of equations, linear system of equations. And the structure of the system is very specific. So it is known that the determinant of matrix A is a van der Monde determinant. And if all nodes of the stencil are distinct, it means that if all x that we use are different, and so this is obviously so, then determinant of A is not equals to 0, and therefore there exists a unique solution to the system, the set of coefficients. Yeah, how many time do we have? So yeah, this is the van der Monde determinant. And so we actually prove the following statement. So if you have this problem of numerical differentiation, so if you want to compute the kth derivative at this node, knowing the values of function of all these nodes, so for a stencil consisting of n points, the method of undetermined coefficients allows one to construct a unique finite difference formula for the derivative of order k. So the k is between 1 and n minus 1 with the accuracy of at least big O of h n minus k. So this is general expression, and we can illustrate it for the cases we have already considered, right? So for better understanding, for example, now we can analyze just the same formula for approximation of the first derivative, for example, u prime. Suppose we know the values of our grid function at this point, and at this point. And we need to approximate the function here. Then we use method of undetermined coefficients. For that, we use Taylor series expansion for this. Just using definition. And then for this, so here h is greater than 0. That is why here h and here h and here minus h. That is why here is minus h, and here is also minus h. And then we write the formula with unknown coefficients alpha, and then we put this guy here and this here. Okay, and also I'd like to compute the second derivative here. So that is why here 1 over h, and here 1 over h squared. And we put this x plus y h here and here, and this here and here. And on this way, we get the same system of equations. So now you can try, as an example, build, for example, numerical approximation, one-sided approximation. For example, if you know a value at point x, x plus h, x plus 2h, try to compute the derivative at point ux, for example. All this is necessary, so it's just abstract example, right? So here u is just some function. It's not, velocity, density, and so on. There's no connection to gas and so on. But it relates to basics of numerics. So this is Taylor series expansion for u of x plus y h, and here u of x minus h with unknown coefficients. And again, we can open the brackets and collect the terms proportional to different degrees of derivatives. So for ux, u prime x, u double prime x, and so on. And so we can hear that the sum of all coefficients alpha should equal to 0, because they correspond to function u. This one, and this one. So we do not have u function to the right of our equation, because we want to approximate the derivative. Alpha 1 minus alpha minus 1 equals to 1, because it's here and here. And we should have the approximation of our first derivative. And the next term, alpha 1 plus alpha minus 1 should equal to 0, because we want to build the most accurate formula. That is why we should not have this term proportional to h squared. And actually that's it. We are not able to, so we have 3 unknowns and 3 equations. We are not able to build more accurate numerical scheme. And so the final degree of our numerical scheme will be not greater than 2. Actually. So we can solve this system of equations and get these coefficients. Alpha minus 1, alpha 0, and alpha 1. So once again, what did we try to do? We tried to build the most accurate formula for approximation of first and second derivative at the point x, take into account value here and here. So we believe that we know the values of our green function at these 3 points, and we need to compute the first and second derivative here. And we get that the most accurate formula of numerical differentiation for the u prime at point x is ux plus h minus ux minus h over 2h. So this is intuitively understandable formula. You may know it, but this is the general theory underlying this formula. So this is a central difference formula. So the accuracy order is second, or big O of h squared, because these terms we do not have them, and the next one is proportional to h squared, but we have h to the first power here. That is why the final term is proportional to h squared. And now we'll try to use this more accurate formula for a solution the same problem that we started with. Yes, and also this is an example of that how can we get the second order derivative. So we can use just the same approach, but now we try to get the second order derivative. And again, summation of all coefficients should equal to 0, because we don't have u. Now alpha 1 minus alpha minus 1 equals to 0, because we want to approximate not the first derivative but the second derivative. But alpha 1 plus alpha minus 1 equals to 2, because we have only we want to have only the second derivative to the right hand side. Okay, we can solve this equation, get the unknown coefficients, and the formula, also well-known formula for the approximation of the second derivative, and it will be proportional to, yeah, specifically in this case to the h squared. Anyway, so okay, I just tried to explain to you that, for example, we took just explicit Euler scheme and substituted du over dx with the first order scheme, explicit Euler scheme. But what happened? What will happen if we'll change it using this central difference scheme? And I try to explain to you the, general approach how to get this central difference scheme. And this central difference scheme is the most accurate one that can be built using points x, x plus h, and x minus h. So only one changing, right? So we just, so the idea is maybe, that, so the explicit Euler scheme is just first order scheme, and the first order scheme, they are not very accurate. Maybe it would be better if we will try to build more accurate numerical scheme. That is why we analyzed and figured out that yes, it's possible to use more accurate numerical differentiation formula like this one. But on this way, we have some troubles. Again, so we introduce the computational grid. We have nodes xn equals to nh and so on. And un now is a grid function. And so we just can rewrite this formula like this one. Suppose what happens if we take n equals to 1. If n equals to 1, then here we'll have u2, here u0, and here u1, right? And the problem is that we know u0. So we know it from initial data, because everything starts here, and we know that u of 0 equals to b equals to 2. But at the same time, we do not know this u1. So this value is unknown. And actually, even again, so I'm trying to show you some typical problems that actually arise in real computations and in real cases, just for very simple problems. So this is just one ordinary linear differential equation and simplest possible numerical schemes. But even here we have a number of questions that actually the same as for much more complex problems. So we know this value, but we do not know this value, and we are not able to start simulations, right? We are not able to compute our numerical solution without, understanding how can we take this u1. And actually, from theoretical point of view, the choice of even of this just u1 is very important for properties of our numerical method. Okay. To understand how can we take this u1 and how does it affect the properties of our numerical scheme, we should consider this as a difference equation. So we can rewrite it and get this one, un plus 1, un minus 1. This object is called a second order difference equation. It's similar to theory of differential equations. The general approach how to solve this difference equation. So once again, for explicit Euler scheme, we also got the first order difference equation, and we were able to build the exact numerical, the exact solution of this difference equation just by, some manipulation of terms and so on. We did not use some general approach. But here the general approach is known. The general solution of this second order difference equation is sought in the following form. So un equals to q to n. Then we obtain the so-called characteristic equation, and q should be the roots of this characteristic equation. So we put the solution, so we say suppose the solution has the following form. Then we put it here, then q to n plus 1, qn minus 1. So we just divide over q to n minus 1 and get this square equation to get the roots of our characteristic equation. So suppose we know the roots, so it's possible to find them. Just the the square root equation. And so let's Q1 and Q2 be the roots of this quadratic equation. Then the solution to the original equation is, and we can write, so similar to just theory of differential equations, we can write the general solution. Here alpha and beta are some constants. We can find these alpha and beta constants from initial conditions and express them using those u0 and u1. How? We can take n equals to 0 and n equals to 1. So if you take n equals to 0, we have u0 equals to alpha plus beta. And if you take n equals to 1, we have u1 equals to alpha q1 plus beta q2. So these are equations to find alpha and beta through u0, u1. Okay, so we find alpha and beta. And if we can do that, we can get the general solution of our finite difference equation. So once again, we just substituted explicit Euler scheme with the central difference scheme, and on this way we can actually do the same things, but now things are much more complex. Not very complex, but anyway. Now we can explore this solution, because again we want to compare it with the exact one. So we still know the exact solution, b e minus axn. But now the numerical solution looks like this one. So it's much more complex in comparison with that just solution obtained using explicit Euler scheme. So we can analyze some asymptotics. So we can solve this quadratic equation, find q1, q2, and analyze what happens if h goes to 0. So if h goes to 0, then q1 goes to unity, to 1, and q2 goes to minus 1. And again, yeah, and we can use the asymptotics for this q1 to n and q2 to n, and again we can use the Taylor series expansion to get these expressions. So we want to understand how the solution behaves when h goes to 0, and to estimate error, just in the same manner as for Euler equation. But for the Euler equation it was very simple, but here is a bit more difficult. And again, we should keep in mind that we still do not know u1. So we know u0, but so we started with the problem that we are not able to use this numerical scheme because we do not know u1. And this u1 can be found, or at least we can recommend how to find it as a result of comparison of our numerical solution with the exact one. So okay, we analyzed the solution of finite difference equation corresponding to the central difference scheme. So we consider the just one linear ordinary differential equation, the Cauchy problem, and we try to understand how the numerical solution corresponds to exact one, and the numerical solution is obtained using central difference scheme. And we applied the actually general theory of difference equations and obtained this formula. And we try and we try to get asymptotics. So we consider the case when h goes to 0, and we try to understand the behavior of this numerical solution when h goes to 0. So all this mathematics is not very complex, but just you need to do that carefully. So now, if h goes to 0, we can analyze this solution, and it happens that figure out that if u1 goes to u0, then this term goes to b, and this term goes to 0. That is why the requirement for the choice of u1 is that u1 should go to u0 when h goes to 0. This is some general requirement. But we can do it in different, so there are several ways how can we choose u1. So options for the u1 choice. So the first, the simplest possible way how can we choose that is to choose u1 like just u0 plus or big O of h. So in fact, we can choose it in C like this one, and the numerical solution will be the exact one plus the term proportional to h to the first power. Or we can propose more accurate way how to choose u1. For that, again, we use Taylor series expansion of function u near x equals to 0 to find UH. And this is u0 plus h, u prime 0 plus big O h squared. And then we take into account that we solve this equation. It's our initial equation. So this is, again, general trick. And we express u prime and put it here and get the relationship between u at point h and u at 0. So u0, 1 minus ah, plus terms proportional to h squared. And we can propose another way how to take u1. It's like 1 minus ah u0. And on this way, you will get the formula with the second accuracy order. So it means that, generally speaking, how can you choose this u1? So it affects the accuracy order of your numerical scheme. So it's not only important to provide high order approximation of your differential operator like d over dx, but it's also important, or at least you should understand that it affects. So you should take into account the approximation of your boundaries, of your equations near your boundaries. They also affect. So this simple example demonstrates that. But anyway, why did we get such result? So for Euler equation, it was b e minus axn plus oh like here. And for central differences, for the appropriate choice of u1, we got the second accuracy order. Why is it so? So the obvious idea that this is because we used more accurate presentation of our derivative. So approximation of the first order derivative with the first order of accuracy is this one. So this is explicit Euler scheme. And approximation of the first order derivative with the second order accuracy is this one, central difference scheme. And that's true. And so the main reason that for that we obtained more accurate result, generally speaking, is that we used more accurate representation of our derivative. But is it enough? So maybe we can just take formulas of numerical differentiation with more and more terms and get more accurate formulas. And actually, the life is much more complex. For example, this is a known example example of a consistent but not stable approximation. Yes, and so this property is called a property of consistency. So the numerical scheme is called a consistent numerical scheme if we use numerical approximation of our differential terms with these properties, with this property. It looks like so it means that our numerical approximation of this differential operators they are reasonable. So indeed our numerical approximations for derivatives indeed approximate derivatives. So it means that actually the scheme is consistent. But I think that next time we'll just plot these graphs to see why is it so. So this is a well-known example of consistent but not stable approximation. So you may think that if you approximate your derivatives in a reasonable manner, that everything will be okay, but actually not. So consider this numerical scheme is just explicit Euler scheme and this central difference scheme. And actually, if we provide some blend, some mix of these schemes, it will also be a numerical scheme. For example, we can consider this weighted sum, y1 minus mu from, and this is explicit Euler scheme, mu, and this is central difference scheme, like this one. And this is also a relevant approximation of the first order derivative. You can check it. So if you add low order approximation scheme to high order approximation scheme, you will get low order approximation scheme. So if this 1 minus mu and mu for any value of mu, you will get some numerical scheme. So actually, you can propose many different numerical schemes for the approximation of your derivative. And you can propose this numerical scheme for mu equals to 4. So just take mu equals to 4. And so just for the same equation that we started with, just this linear ordinary differential equation, you can propose this numerical scheme with this guy as approximation of the derivative. And this is a relevant approximation of derivative. You can check it. But if you will try to implement this numerical scheme, you will see that it will not work. So you can find the solution of this difference equation like in the same manner we have done for central difference. It will look like this one. And it's the exact solution plus something. And the problem is that this numerical solution is not stable. So the result will be bad. It means that the consistency is not all. There's another very important property of numerical schemes called stability. And now we can move towards. So it was just one example, and we analyzed all properties just in one point, right? So we took just one xn, and we analyzed the error between numerical solution and exact solution just in one point. But the problem is actually that even in this case, you have the whole segment, and you have the whole function, and the function behaves differently in different parts of your computational domain. And that is why we should give more general definitions. So in this theory, we should define, so let's LU equals to F denotes our initial difference problem. So for example, so L is a differential operator. It's just a abbreviation. So for example, for the problem under consideration, LU equals to our equation and also initial conditions, and also F equals to 0 and B. It's just this symbolic representation of our initial problem. So let D be the our computational domain, or not computational but physical domain. So this is our initial problem. So D is the segment between 0 and 1, and then we introduce objects from our numerical world. So DH is our computational grid. So we provide division of our segment with these nodes, x from 0 to n. LH is a numerical approximation of our initial differential operator. And U with superscript H is a numerical solution. And FH is also a numerical representation of right-hand sides. So for example, LHUH now equals to this term for explicit Euler equation. I didn't write it here. So LHUH is this one. The next object, so we understand that we must be able to compare the numerical solution, UH, with the exact one. So let's introduce the exact solution, U in square brackets H. So this object is a set of exact solution of our equation in nodes of our computational grid. So we have our computational grid, and for each node we know the numerical solution called denoted as UH, and this UH is the exact solution. And once again, we need to be able to compare one with another. But now we must do it not in one point to another point. We should somehow do it in whole. And for that, that is why here people usually use norms. Maybe you also know them from mathematics. So in just a line, we can compute the distance between 2 points using just one value minus another. But in space, for functions, we should somehow compare two functions. For that, we should submerge these functions in the space of functions and introduce norms between to compute the distance between functions. So I can remind you that for example, we can start with the scalar x. So the absolute value of x means the size of x, right? With the known properties. In such a manner, we can consider vector x. So the norm measures the size of this vector x, and we can propose different norms of this vector. And in the same manner, we can propose the norm for a function that also similar to norms of vectors. And for example, the simplest possible norm for comparing functions is just maximum value. That is y or supremum. So we should think of this function UH as function in some space U capital H, and we should propose some norm in this space to be able to compare different functions, different numerical solutions in this space. The simplest possible is that on this our segment we find the maximum value of our numerical solution. This is one of possible norms of function that can be used in theoretical analysis. On this way, we can, formulate more accurate definition of what we are going to obtain. So the title of this lecture is Basics of Numerical Schemes. So the first one of the most important properties of numerical schemes is convergence. So the solution UH, so I explained to you that means it stands for numerical solution at each point of our computational grid. Of a finite difference problem, LH UH equals to FH. So I explained to you that this is the abbreviation for our finite difference scheme. Converges to the solution of the differential problem, and this is our initial problem. So this is initial differential problem. This is its numerical approximation. So the solution of finite difference problem converges to the solution of differential problem if this norm difference between exact solution and numerical solution goes to 0 as h goes to 0. So this definition, it's the generalization of just consideration of one point at which we measure the difference between the numerical solution and exact solution. In case of, so when we have the whole segment, we're not able to, compare the solution just in one point because we have many points, and that is why we should introduce the norm how to compare, these functions between each other. For example, as I told you, so this norm may have the sense of supremum. So we have the for example, here we measure the difference between these 2 points, right? Instead, we can take each point and compute the difference between these points, between these values, and take the maximal one. It will be the norm. So on this example, I try to explain to you the general definition that I provided. Here we also can compute the difference between, compute the numerical result in each point and take the maximal one. And you can see that this maximal value becomes smaller and smaller. So this supremum or maximal value behaves like in this example, like the error in each separate point. But if you take it for all points, it will norm, and it can provide us to give some general definitions for terms of convergence, consistency, and so on. Okay, so now we measure it not in one point, but we take into account the whole segment. This is just an example of what did I mean. If the following condition holds, so if this norm of difference between exact solution and numerical one is less than C1 HK, where C1 is some constant and K is constant, then the convergence has the order of accuracy HK, or equivalently, the numerical scheme has kth order accuracy. So it's the same as it was for Euler equation. So we got that this delta was an order of magnitude H. So it means that K was equals to 1, and it was the first order scheme. But generally speaking, so it can be H to kth power convergence. So as I told, the problem is that we do not know exact solution. So that is why we are not able to estimate the property of numerical scheme. For example, we have Euler scheme, explicit scheme, or central difference scheme. Yeah, okay. So previously we were able to compare numerical solution and exact solution. But what if we do not know the exact solution? How can we estimate the property of our numerical scheme? Let's discuss some general idea of how can we build a convergence scheme. So suppose we have our numerical scheme. So this is the schematic representation of our numerical scheme. LH, UH equals to FH. Now let's substitute the UH with the exact solution. So UH is the exact solution, or more accurately, so it's the set of values of exact solution at our grid points. It's the exact solution of our initial problem, not the finite difference problem. That is why when we place it here, we will get some delta F, because once again, UH is not the exact solution of this problem. UH is the exact solution of our initial problem, initial difference problem. That is why even if we put the exact solution, so the best one, the correct solution to here, we will still have some error. So this error is called truncation error. So this term is very important. So truncation error is an error that we obtained when we put our exact solution to the finite difference scheme. Then we can express this truncation error like LHUH minus LHUH, where so this is the exact solution and this is the numerical solution. And so the idea is the following: how can we understand that our numerical scheme LHUH is a good one or bad one? I mean, does it provide the good numerical solution or not? So the idea is following: the general idea, the scheme is convergent if, so first, df goes to 0 as h goes to 0. So the scheme is convergent if this truncation error goes to 0 as h goes to 0. So when we put the exact solution to our numerical scheme, the truncation error should be small, right? So it means that indeed our numerical scheme should be consistent. So it means that indeed our LH finite difference operator indeed approximates our finite difference problem. But it's not enough. This delta F makes little difference to UH. So it means that when you have some, so we can consider this delta F as some disturbance of our finite difference problem. And the problem is that nobody guaranteed us that this finite difference approximation is stable to small disturbances. So the second requirement is that delta F does not change significantly the numerical scheme. So our finite difference operator should not change drastically when we have some disturbances to initial condition, to boundary conditions, some errors, and so on. So the first one actually, so this is the consistency requirement, and this is the stability requirement. So consistency means that our finite difference approximation is reasonable, is relevant, and we can check it using formal analysis like we have done it when we analyze, for example, schemes of numerical differentiation using undetermined coefficients. So the first requirement can be checked using your pen, pencil, and paper. But the second one is much more difficult. You must be sure that, and usually always it's not possible to check analytically, and that this delta F makes little difference to UH. So this is general theory for sure, and also I'll tell you later that all this is only for linear problems. So all these concepts cannot be directly applied for gas dynamics and so on, because these systems are very, 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 very difficult and complex. But nevertheless, these concepts can be extended to nonlinear problems. But this is maybe the most important idea, right? How to build a convergent scheme. So the relevant approximation of our difference operator, plus understanding that this approximation should be stable. So delta F makes little difference to UH. Example. So everything is much more simpler when we have examples. Again, so we consider this problem. du over dx plus au equals to 0. A is constant. Consider, for example, explicit Euler scheme, this one. For this scheme, we can, yes, get the exact solution and compare it with the numerical, but suppose we do not know exact solution. And we want to check if this numerical scheme is convergent and good. How can we do that? How can we check that the truncation error is small enough? We say, okay, so here u with subscript n is the grid function. So it's not exact solution, it's not a continuous function, it's the grid function. Now we say, okay, let's put here u, where u is the solution of our equation. Okay, and now U is non-grid function, is the solution. And on this way, we can use Taylor series expansion again. So we put here, so this is Lu equals to F, our initial differential problem, and this is LH, UH, FH, our finite difference scheme. Just again to explain to you what does it mean, our abbreviations. And we put the solution U here, and now we can use Taylor series expansion. Again, Ux plus H, we substituted using Taylor series expansion. U and U, they goes to 0. U prime, H over H, just U prime. AU, then U double prime, H squared 2, plus big OH squared, because we have two H cubed, and so on, okay? And so, again, typical trick, it equals to 0 because we solve our problem. So the consistency is checked on the solution of our problem. So it's again typical statement that we check the consistency of our problem on the solution for the solution of our equation. Here U is the solution. It means that U prime plus AU equals to 0 because here we solve our solution. And then we get something at rest here. And this term is proportional to H to the first power, and this is delta F. So explicit Euler scheme provides the consistent approximation. Indeed, we can show theoretically that this delta F that we have when we put the exact solution to our numerical scheme goes to 0 when H goes to 0. And so the first requirement is fulfilled. It's possible to show theoretically that it's stable, but actually usually people check it on practice, that indeed the numerical scheme is stable. So this is the general way how to check that the numerical scheme is convergent. Now we're able to provide the strict definition for consistency. So the difference scheme is consistent with the problem if this truncation error goes to 0 when H goes to 0. So as I told to you, so this first requirement is called, so if it's valid, it means that our numerical scheme is consistent with our initial differential problem. If the following condition is valid, so this truncation error is less than C2H to K, with C2 some constant greater than 0 and K is constant greater than 0, then the scheme has the accuracy HK. So as you can see in the definition of convergence, we had the constant C1 and here the constant C2. That's not just coincidence. So we move towards the proof of the main theorem of it's called numerical main theorem of numerical mathematics, so different names. So this is definitions of consistency. And now we should define, so formally the last one, the last requirement. Delta F makes little difference to UH. How can we do that? There are two different definitions. Two different definitions correspond to two different schools, two different, researchers who explore these topics. So these topics were studied in Soviet Union in the 50s and 60s, and researchers from there provided, very generally complex theory of the stability of numerical schemes, and they published, huge books. In the United States, the same Peter Lax, we have discussed Lax entropy condition last lecture. It was conditioned to how to choose the correct solution of Hopf equation. He also developed the theory of stability of numerical methods. And so there are two different definitions based on different points of view. So this definition is a Soviet definition. So the scheme is stable if there are, what does that mean? If we provide some disturbance, to our numerical scheme, and the disturbance is limited, so it's not some huge, it's small disturbance, and the solution of it means that a small disturbance of right hand side of numerical scheme makes a little different in solution. So we provide the solution, and so we provide this disturbance, and the solution of this problem exists, and the norm of difference between numerical solution of our initial problem and with the disturbance, they are small enough. They are less than C3, and the norm of this disturbance. So the idea actually is clear. So the small disturbance should not change your numerical solution significantly. This definition is United States definition. It uses the knowledge that our operator LH is a linear operator. The differential scheme with linear operator LH is stable if your numerical solution is bounded. So it means that stability is equivalent to that your numerical solution do not blow up. So it means that your numerical solution should be bounded. And so actually it's possible to show that definition number 1 and definition number 2, they are equivalent. I don't think that it's, so I can do it, so it's that's not very interesting. So you should know that actually there are different definitions. So actually this, so the first definition is more, it corresponds to definitions of well-posed problems from mathematical physics, right? And this definition may be more practical because it corresponds to our general understanding from simulations. So what does it mean that your numerical scheme is unstable? Because from some instant you will get not the numbers in your simulations. So you get some graphs, some plots, and suddenly your numbers in your files, instead of these numbers, you can see N means that something goes wrong. So it means that very often your numerical scheme is unstable. It means the numerical solution becomes, unbounded, so infinitely large. Two different definitions. So the first one can be attributed with the name of Ryabenkii. It's a Soviet and Russian scientist. I didn't change, right? He died this year, as I told to you. So the first definition attributes to Godunov, Ryabenkii, the Soviet scientists, and again Godunov's scheme. We will discuss it, but Godunov also contributed to to this definition also. And the second definition is more about works of Peter Lax. And so now we discussed that the numerical scheme should be so there's the concept of convergence, consistency, and stability. And I told to you that the numerical scheme is convergent if it is stable and consistent. And this is the essence. So this is the brief historical information of Ryabenkii. He also is a veteran of the Second World War, and he worked in 1952. But the problem again is that he published all the books only in Russian. It was like books in Russian, and they were in libraries of Institute of Academy of Sciences, and no one foreigners even knew about anything about that. And only in 90s, although no, they were able to meet each other even during Cold War. Some Americans, they went to Soviet Union. I think not quite contrary. And for example, Godunov and Lax, maybe they met. I didn't remember. But Ryabenkii and Lax met in 90s, or in even the beginning of 21st century. But the problem is that for a long time their works developed independently because of politics and that time. This theorem is known in world literature as Lax Equivalence Theorem. Nobody said Lax Ryabenkii theorem. Only in Russia it's called Lax Ryabenkii theorem. So the whole world, name it Lax Equivalence Theorem. What does it mean, equivalence? So we're assuming that the numerical scheme is consistent with the problem, our initial difference problem, with the accuracy h to k and stable. So we assume the numerical scheme is consistent and stable. So we discussed what does it mean consistent. It means that if we put the exact solution here, we will get the truncation error that goes to 0 when h goes to 0, and stable. So it means that small disturbances of this operator does not change significantly our solution. Then the solution of finite difference problem converges to exact one. And these constants C2 and C3 are those constants from definition of consistency and stability. And the proof is not so difficult. Actually, we have everything in hands. So we have the definition of stability, and we have the definition of consistency. In the definition of consistency, actually it's simpler to explain here. So we can consider this delta F as the disturbance of our numerical solution in the definition of stability. And the exact solution in this is the disturbed new solution of our finite difference method. Okay, so we can just consider the definition of stability, and here in definition of stability, this disturbance, we consider the truncation error as a disturbance in the definition of stability. And then we can apply this formula, and then this formula, and easily get that the norm of difference between the numerical solution and exact solution less than truncation error, and this in term is less than C. So because of the stability. So by combination the definitions of consistency and stability, we can prove actually that scheme is convergent. Why Lax Equivalence Theorem? So because we can think about the convergence of numerical scheme is equivalent to stability. So for a consistent numerical scheme, for a reasonable approximation of your derivatives in your equation, so if the approximations are reasonable, then the convergence is equivalent to stability. That is why this theorem is called Lax Equivalence Theorem. And as I have told you, the problem is that everything here is valid for a linear operator L. So what does it mean, linear operator? It means that Lu plus L some other function V equals to Lu plus V. So this is all these concepts are valid only for linear problems. For nonlinear problems, it's possible to have to generalize to somehow these things, but if you consider shock waves, strong nonlinearities like an Euler equation, all this doesn't work because of discontinuities. Actually, it's obvious. So when you compute the flow with shock wave, you have some points because of differentiation through the discontinuity, and you can take smaller computational mesh, but these points are still so there will be still big gaps in the vicinity of this discontinuity between the exact solution and numerical one. So the discontinuities, they prevent you from application of all these concepts, and you should use another definitions of stability, nonlinear definitions of stability, TVD criterion, and so on in the nonlinear case. But anyway, even for example, if your research will be not about complex nonlinear problems, this theory is very important because it's valid for any numerical approach for the solution of ordinary differential equation. And in a lecture, in 2 lectures, we will discuss the development of all these concepts for partial differential equations. So actually, once again, it was just ordinary differential equation. We have only one variable x, and for the partial differential problems, we have t and x, and in that case, we have accuracy in time and accuracy in space. So the things much more difficult, and many concepts are similar, but not all, and they should be developed for partial differential equations. Okay, I think that's enough for today.